Week 3's podcast time, guys. So, let's not hang around and waste any time. Lesson 13 saw us go over one very brief thing before we looked at exam skills. So this was storm surges as shown in the picture of this video. This right here is a storm surge. Okay, it's an important aspect of tropical cyclones and low pressure weather hazards that they generate multiple hazards. So when they hit the land, the very strong winds are just one of those hazards. A storm surge is another. So the low air pressure at the center of the storm increases sea level by 1 centimeter for every 1 millibar drop in air pressure. As the cyclone moves towards the land, the bulge of water, these big waves created by the storm surge, is pushed onto land, causing widespread coastal flooding to both property and crops. You can also have this series of waves, but another thing you can have from cyclones is landslides, intense rainfall and winds. All three of these coming as a result of tropical cyclone conditions. After this, we looked at a bit about exam skills. I will cover this in this podcast. So the first one is about a 10 marker. So 10 markers are still essay questions. Okay, they look for a clear expression, coherent argument, an argument that makes sense, making sure that you use effective grammar, punctuation, spelling, and use all of the appropriate geographical terminology. So what I mean by that is your keywords in your glossary and in the right way. If your question requires assessing or evaluation, you'll have to make sure you make an argument, potentially a balanced one that looks at different points of view and different data-influenced outcomes. When a marker is marking a 10-mark question, we are looking for AO1 and AO2. AO1 being your knowledge and understanding. In other words, do you understand the core geographical concepts? Have you got the right case studies? Are you using the relevant case studies to this question? Have you got the right examples? Do you understand the processes? You are showing off what you know, but also everything that you know that is relevant to a particular question. AO2 is how you apply your knowledge, how you apply your case study to actually answering the question and analysing the question. So this is where you apply your knowledge to a specific question using the relevant examples and show how different factors interact. Okay, with evaluation and judgment questions, there may be a hint of AO3 for making a judgment and a conclusion. But don't forget to use clear structure. An introduction can be 2 sentences long. For the 15 marker, it's the same as well, to be honest. An introduction, I would say, needs to do 2 things. It uses the wording of the question, and then it defines any keywords in the question, as well as maybe bringing up which case studies you are going to use in that answer. Okay, but that can be done in 2 sentences very easily. In terms of a 10-mark question, how we mark it is we level mark it. So I will read an answer. When I mark your work, I'll take your work and I'll read it and think, right, is it level 1, 2, or 3? If it's a level 1 answer, if it demonstrates isolated things as being correct, some of it is inaccurate, some of it is irrelevant, if I think that you haven't actually got that much limited information, then I would say that your answer is a level 1 answer. So your mark would be between 1 and 4. If I think actually there's some understanding here, it's mostly accurate, it's good, it's written well, and there's some partial argument here, I might give it a 5, 6 or a 7 mark, a level 2. To get into the top band, which is what you should all be aiming for, to get a level 3, to get 8, 9 or 10 marks, I would need to see accurate, relevant, geographical knowledge and understanding throughout. That's the AO1. The AO2, you have to apply knowledge and understanding to a logically and fully relevant case study. You'd have to also produce information and ideas that make an argument that is supported by lots of relevant and accurate evidence. Okay? In terms of 15 marker, it's a little bit different, but the idea is the same. Definitely have an introduction, definitely have your appeal paragraph, your point, evidence, explain, and link. Like I told you in class, a point should be 1 sentence. Your evidence is probably 2 sentences. Your explain is up to 4. It could be more, but 4 should be enough if they're succinct enough. and then the link is 1. So if you structure your paragraphs in the 1, 2, 4, 1 structure, in other words, 8 sentences per paragraph, then I think you're laughing. You're on the way to a good score, that's for sure. Okay. In your 15 marker, again, we're looking at the AOs, we're looking at strong arguments, we're looking at specific examples, we're looking at using a clear case study and demonstrating a clear understanding of the topic while making a coherent argument to the examiner. So for 15 markers, it's the same kind of thing. Level 1 is 1 to 4 marks. Isolated, irrelevant stuff, not fully on topic. Level 2 is 5 to 8 marks out of 15. So demonstrates some understanding, occasionally relevant, a little bit limited the answer is, okay? Some evidence. If your answer has some stuff in it, I'd say it's level 2. Level 3 is mostly relevant, maybe some inaccuracies, but mostly good, mostly logical. There is an argument there. But again, maybe it's a bit partial. To get to the top band, to get 13, 14 or 15 marks on level 4, that's where I would look for accurate and relevant geographical knowledge and understanding throughout. It's the exact same wording for the 10 marker. Okay, that's your AO1, and your AO2 again is applying an understanding of geographical information, making the relevant connections and relationships, again supported by full amounts of evidence. So if you're reading through your answer that you've written for me, and you can think, right, yeah, it is relevant, it is accurate, it is detailed, it is coherent, it makes sense, there's a clear argument here answering the question, then you should be in the top band. There's no reason why you wouldn't be. Okay? In terms of section A in previous years on weather and hazards and atmosphere and weather systems, there are 2 questions. Normally a 10 and a 15 marker. I'd say it's about half an hour of your work, including some planning time. So we'll get down in terms of how you write answers quickly. But for now, it's about getting the skills, making sure that you structure it in the right way and tick all the relevant boxes to get to the top level, which is what you should all ultimately be aiming for. In terms of our next lesson and forecasting weather, evaluation tables, this was looking towards eventually writing a 15 marker. Evaluate the contribution that forecasting technologies can make to successful management of extreme weather events. So forecasting, how you do it, let's evaluate. Satellites, what satellites do is they observe the atmosphere from space. They're good because they are large scale, they cover a large area, and they are continuously monitoring 24/7. However, a limitation of satellites is they limit local detail, so you can't see what a specific town might be like compared to a neighbouring town, for example. It's more for the greater good, the wider number of area. Ground stations, these measure conditions at surface level, and they are accurate. However, in remote areas and even LIC areas, they are sparse. You can't have ground stations everywhere. So in areas where there isn't many people, they haven't got many ground stations, if any, in some places. The radar you can use. Radars detect rainfall, precipitation, and movement, and they offer real-time data. They have accuracy in the short range. However, it is only short range, therefore they can't really cover anywhere longer distance, and also can be affected by terrain. For example, mountainous areas are difficult to measure. And computer models. Computer models simulate future conditions, and they offer medium-range forecasting power, which is quite good in terms of looking over the next few hours or days. However, they are limited to long-range precision. So what I mean by that is long-range precision is limited. You can't always do this for multiple days/weeks, because it's very hard to predict weather. It can be very temperamental. You then had a timeline which looked at the development over time of different technologies, and clearly it has evolved over time. We used to rely on sundials and stuff like that, and now we have all this tech that we are using to the fullest to hopefully help us ultimately predict tropical storms, predict weather and extreme weather events, because this prediction can help with warning people and evacuation, like cyclone shelters, hazard-resistant design. All these things are responses to tropical cyclones, and they are varied in terms of success across the world. Developed countries versus emerging countries are going to have different impacts. Okay, then you answer some questions based on the reading, but ultimately you can see, long story short, that accurate prediction and early warning allow time for evacuation, and this happens more in HICs because they have better communication technology and better monitoring technology. Okay, with better evacuation and more quick evacuation and better resources, you can therefore reduce the impacts and hopefully reduce the amount of casualties and damage to infrastructure, giving more time to prepare and batten down the hatches. However, it's also important to note that early warning and accurate prediction doesn't always mean the effects are going to be less. Because don't forget, the intensity of the storm, the time of day it happens, are both factors that can impact that regardless of how wealthy a country is. But traditionally, developed countries typically do have more accurate forecasting tools, more reliable infrastructure, and strong governance systems, which mean that they have a more successful response on the whole. Developing nations often lack these resources, though they have low-cost community responses. They could help with proper planning, but are much less likely to do so. It's also important to note that if the public trusts the authorities, they're more likely to comply with evacuation orders, because not everybody can be evacuated or indeed wants to go. Distrust can lead to non-compliance, and that increases the risk to life from certain weather events. Then we looked at assessing real forecasts and how you can display different weather forecasts, whether it be over the days, whether it be through graph form, whether it be through different time scales, so days, weeks, months, and even over the season. Anyway, there is a summary table that you completed of forecast accuracy. And ultimately, again, long story short, over time, things get less accurate. So if you're forecasting over 1 to 3 days, that's considered a short term, and you're normally about 90% accurate in terms of temperature, so within 2 degrees. And in terms of rain, 85% of the time you're going to be correct. There's nowhere that's 100% correct. So the example for short-term weather is the UK Met Office. Every day there's a weather forecast, and the UK Met Office provides that data. Medium range forecasting, looking over the next 4 to 7 days, is down to 80% within 2.5 degrees Celsius. And in terms of precipitation, it's down to about 70 to 80% of the time correct. The ECMWF in Europe looks at weather in the medium range and tries to forecast. Over a week is considered long range, so anything over 7 days, and you're down to about 30 to 50% skill over climatology. And in terms of precipitation, again, it's variable. It really is variable. The NOAA in the USA is evidence of this. Okay, tropical cyclones, you can track them up to 3 days with 90% accuracy, but there can be an intensity error. Sometimes they can be under or overrated in terms of their speed. 10 knots, the NHC, the National Hurricane Center, being the example for this one. But in developing regions, compared to 90% before, you're looking at now 60 to 70%. And this could be over 24 hours rather than 3 days, because the technology is simply not there. With rainfall, precipitation, 60 to 70% rainfall accuracy, and again, our example for that was indeed Bangladesh. Okay, and then you wrote your 15 marker with the same structure, the 1, 2, 4, 1 format. Okay, you walk using wording of the question, intro, peel, and conclusion. Okay, because the aim for this lesson was to be able to discuss the importance of prediction, warning, and evacuation as responses to tropical cyclones, and also how these vary in terms of success across developed, developing, and LIC countries, ultimately. Okay? And then towards the end of the week, what we looked at ultimately, again, was comparing LICs and HICs in a lot more detail, with our objectives being to evaluate named weather hazards and the responses to them, understanding the role different groups play in managing these extreme weather hazards. So whether that be the government using land use zoning, maybe first responders, community groups, NGOs/charities, and other aid organisations too. Now, land use zoning against flooding from tropical storm rainfall or storm surges involves restricting certain developments in flood-prone areas to reduce risk by guiding development and to safe locations, regulating building practices, and promoting land uses that minimize impact. Ultimately, you are building only in safe areas. If areas are prone to flooding, if areas are likely to flood, by land use zoning, you just don't build there. Okay, high risk zones typically limit or prohibit construction entirely, so you'll have to build maybe a little bit here or not at all. While moderate risk zones can allow for development, however, they have to have flood resistant building codes and green infrastructure to do so. Okay, now this approach is non-structural mitigation strategy, so it tries to reduce the impacts and it balances the safety, economic needs and environmental protection of an area, and I showed you a diagram of what that looks like. Okay, in terms of your examples for this lesson, it was Boscastle 2004 HIC, and your comparison was with Mozambique and Cyclone Idai in 2019. And in this lesson, we looked at the name of the case study, but also the location where it happened, when it happened, the technology used, the causes, the primary impacts, the secondary impacts, the primary responses, secondary responses. Don't forget what happens first and what happens afterwards. Who is in charge for monitoring here, what was done well, what could have been improved, and the overall evaluation using different statistics. And ultimately, what you found is Cyclone Idai was a lot more devastating than Boscastle. Doesn't mean that Boscastle wasn't devastating, but they certainly, although not fully prepared, had better technology to be able to deal with such things. And land use zoning was one of those examples. Okay, and when you did that, you made a table, so you have that on you as well. And then we started to look at even more of protecting ourselves and the role of engineering. Now, for your homework, you looked at soft engineering. So soft engineering is where, I mean, spoilers if you haven't done your homework yet, but soft engineering is where you use natural and non-intrusive methods to protect yourself from tropical storms or anything, floods or earthquakes, whatever. But in this case, tropical storms. Whereas hard engineering is using artificial man-made built structures that are more intrusive, but often more reliable and more expensive as a result. So, in terms of engineering against weather extremes, there are different types of hard engineering: levees, flood walls, and embankments. Okay, all these things can help reduce the impacts of tropical storms that may flood rivers or surrounding areas. Okay, so soft engineering, natural, low impact, sustainable flood management strategies such as afforestation, wetland restoration, floodplain zoning. So again, just deciding not to build somewhere is soft engineering. River restoration, early warning systems, and sustainable drainage systems. All these things help a community to be more prepared, and that's soft engineering because nothing's been built. Okay? But then we looked at levees. A levee is a hard engineering example because it's an embankment deliberately built by an artificial structure, by a man-made company, to prevent the overflow of a river. And this can be used in terms of with tropical storms, because obviously with the extra rainfall, rivers can rise in terms of their discharge, sometimes to a dangerous level. And we looked at the pros and cons of levees. So ultimately, they provide local flood protection, they contain the flood waters, and they help with allowing buildings to be built either side. They offer economic benefits because they can obviously reduce the likelihood of costly damage. And some modern ones even help with biodiversity. You can have trees on them, which is quite important. Okay. However, there are significant negatives. They pose a risk of catastrophic failure because if they overflow, then there's nothing else you can do. They also lead to rapid and severe inundation. They can also increase the river downstream. If you're solving the problem where you are, it means directing it to somewhere else further down the line, which can mean the effects are worse somewhere else, because the river level can be higher. They can also damage the environment. As much as they can be environmentally friendly, they can actually reduce biodiversity if built off wrongly, and also lowers public awareness of flood dangers, because if they're there, it's taken for granted. A flood wall is a similar kind of thing. It's a permanent freestanding and engineered structure, typically made of concrete. designed to act as a barrier simply to prevent floodwaters from going into an area. And again, they have positives and negatives. So it's strong, it's durable, it lasts a long time, sometimes generations. Okay, they do work. They don't look very nice, which is a bit of a negative. They can be, uninspiring, but they can also be blended into the wildlife as well. But they are also very expensive. And for health and safety reasons, they require constant inspection. They may last a long time, but you can't simply build a wall, just leave it there for 50 years. You have to keep checking it to see if there's holes, see if it's damaged, and keep repairing it. And maintenance is very expensive too. They are limited to how high they are, so the higher the wall, the more they protect. So it depends on how high a wall is, depends on its effectiveness. But again, if you're saving yourself, it's similar to levees. If you're saving yourself in an area, this means that further down the line, further downstream, the impacts are going to be worse. Okay, with a big wall there can be a false sense of security. People who live near flood walls might think, "Oh, we're definitely safe," where actually it could still be a problem. And an embankment. An embankment is a wall or bank of earth or stone built to prevent a river flooding an area. And again, it's very similar. Okay, so embankments are very effective. They are quite simple. They're very cost effective. They last a long time, but also, they may be expensive, but they do cost enough to make it worth doing, especially if you can afford to do it, like a HIC. So like maybe they might be more engineered than the flood walls, for example. They can be designed to blend into natural landscape. They can be vegetated. They can reduce erosion. And they are very useful in rural areas where maybe there's farmyards either side. However, there are risks, there are challenges with everything. They are susceptible to erosion. So, for example, they can get eroded very quickly if a river is moving fast, if there's high amounts of discharge. They can overtop. If they're not maintained very well, they will literally fail. Embankments can collapse suddenly without much warning. As a result of this, they can reduce the risks of flooding, but also can reduce the land's capacity to absorb floodwaters, which might increase the risk further downstream. And again, there's this false sense of security. So yeah, it's a tricky, different measure in terms of embankments. Okay. Levees cost between $500,000 and $2 million per mile. Flood walls are between $2 and $10 million per mile, and embankments can be down towards $300,000 to $1 million per mile. All very expensive. I'm sure now you're starting to see actually why LICs can't always afford these protections. Okay, maybe the soft engineering methods of afforestation that I mentioned earlier, or maybe the other examples of simply not building somewhere, floodplain zoning, or giving as much early warning as possible is a cheaper, although less effective approach. And then we ended the lesson with looking at a plenary of how an 8 marker might look. A 10 marker might look. Evaluate the effectiveness of soft engineering strategies in reducing flood risk from tropical storms. So with that kind of question, you'd only focus on soft engineering because the question says so. Remember to read the question carefully. My most important bit of advice ever. Any questions, let me know. I'll see you for the next one. Take care.